Hey guys, what's going on? In today's video, we will be doing backpropagation. So I'm going to be doing it manually by hand with a small neural network. Then I'm going to be doing it in the matrix form as well and show you how that's done. Then after that, we'll move on to code. And in the code, I will show you how to do it using NumPy. We're going to create a neural network just using NumPy and then compare it to the same neural network but using TensorFlow. So before we get right into it, here are certain prerequisites that you have to know. So the first one is derivative calculus. You need to know how to differentiate, you need to know the chain rule, and you need to know the derivatives of certain functions. And the second one is basics of linear algebra. And by that, I mean you just need to know how to do matrix multiplication. So let's get right into it. For our data set, we're going to take something pretty simple. So if you can see right here, this is a sphere, only the upper hemisphere of it. So what we're going to be doing is our data point is going to be points on this specific sphere. So what we're going to do is I'm going to show you the equation of a sphere. So it's x squared plus y squared plus z squared is equal to r squared, where x, y, and z are your coordinate planes, and r squared is the radius of the sphere. So we're going to take two inputs. So our neural network is going to take two inputs, our x and y, and our target is going to be the z variable, and we're going to fix the radius to something constant. So over here, I'm going to take radius as 5. So if we rearrange the equation, we get z is equal to r squared minus x squared minus y squared. So here we're going to substitute r squared to be 25 because 5 squared is 25. So what that means is, so this is going to be our data set. We're going to have x, y, and z. So x, we're going to take, suppose we take x as 1. This is our construction of the data set, by the way. So if we take x as 1 and y as 1, that means our z, which we will compute, is going to be square root of 25 minus 1 minus 1 squared technically, minus 1 squared. So this is going to be square root of 23, and that will be whatever. So this is how we're going to calculate. We're going to take random points of x and y, and we're going to calculate the z using this formula and populate our table, and this will be our data set. Now let's move on to the neural network architecture. Now here is the neural network. So as we can see, instead of using x, y, and z, what I'm going to do is I'm going to name x. So what I'll do is I'll consider x. Instead of taking x comma y comma z, I'm just going to transform this to be x1, x2, and y. So this is our target. These are our features. So we got x1 and x2. Then we're going to connect the layer. So we've got 3 neurons in the hidden layer, each with their corresponding biases. This is A1, A2, A3. This is our final output neuron. It takes a bias, and we got y cap, and y cap is our neural network's prediction. So what I've done here is we're going to be using the tan h activation function for the hidden layer, and the output layer will not have any activation function since it's a regression problem. So let me just expand on the notation a bit. So in x1, we can see the weights associated. So it's going to be W11, W12, W13. So W1, since it's associated with X1, and the second one that comes is because it's the first neuron. And for the second neuron, it'll be W12. So similarly for X2, it'll be W21, W22, W23. And this top part over here, this one in bracket, represents which layer we're in right now. And for our, so how is it going to look? So what will be the output that comes out of here, this blue line? So the output A1, as we can see, we've got W11 coming, W21 coming, and we've got its bias. So A1 will essentially just be, since we're using tan h activation function, it'll be tan h of W11, and W11 is associated with what? It's associated with x1 plus W21, and what is that associated with? That'll be x2 plus our neuron bias. So that will be A1. So similarly, A2 will be W12, W22, and B2 instead. And finally, our output y cap, if we go up and look at it, so we have the weight associated with this to be W1, since it's second layer, we got 2 in brackets. We got W2 with respect to A2, we got W3 with respect to A3, and we got our bias. So our y cap will just be A1, W1, this is the second layer, plus, and this will be, I'll just name it 1, A2, this is 2, W2, plus A3, W3, this is 1, this is 2, and yeah, this will be 1, plus our bias B, second layer. So this is our output of the model y cap. Now I'm going to move on to the forward parts of this using just this algebra method, and then after that we'll be talking about the matrix form of this. All right, so here I've cleanly written it out. So AJ is the hidden layer neuron. So J is 1, 2, and 3 because there are 3 neurons. So this is a generic way of writing it. So A of J is tan h of W1J plus W2J plus the bias associated with J. Then our y cap is going to be W1, A1 as shown earlier. So now what we're going to do is we're going to take only one sample. So for the first sample, we're going to assume that x1 is 1, x2 is -1, and y, technically it's square root of 23, but we're just going to take it as 1 for now for simple calculations. Then we're going to initialize our weights. This is just a random initialization. So W1 I've taken as 1, 2 1 is 0, B1 is 0, 1 2 is 0, 2 2 is 1, B2 as 0, 1 3 is -1, 2 3 as 1, B3 is 0. And for our output neurons, the weights we're just going to take 1 and we're going to take the bias as 0. And our loss function will be defined as half of, we're going to take, let me see, y minus y cap the whole square. So we're going to take this as our loss function. So since it's only one sample, we're just going to calculate loss associated with one sample. But say there were 300 samples, you would repeat the same steps 300 times, but for that specific input x1, x2, and you would sum up the losses. That's what you would end up doing. So without further ado, let's start writing it out. We're going to go through this manual forward pass. So yeah, let's do that. So from our formula, we're going to write A1, A2, we're going to get A1, A2, A3. So A1 is W11 X1 plus W21 X2 plus B1. So, and tan h of this. So what is that going to, that's going to look like tan h of tan h, W11 is 1, 21 is 0, and the bias is 0. So it's just essentially just going to be tan h of 1 into x1 we have taken as 1. So it's going to be tan h of 1 star 1 plus 0 plus 0. So it's going to be tan h of 1. And this, let me just take out my scientific calculator and just tell you what that is. Yeah, this is going to be 0.76. Similarly, we're going to get A2 and A3. So again, just substitute the formula. A2, once we substitute it, will ultimately get tan h of -1, which is approximately 0.76, negative 0.76. And our third, A3, is just going to be tan h of -2, which is approximately negative 0.96. So now we're going to calculate our output. Our output y cap is going to be A1 W1 plus A2. I'm not going to write the layers because that'll just take too much time. By layers, I mean specify that this is 2. I'm not going to do that so that we save time. And our bias. So this is, since W1, W2, and W3 all are 1. So it's essentially just A1 plus A2 plus A3 plus B. So this is going to be 0.76, negative 0.76, negative 0.96. And what did we take the bias as? We took the bias as 0. You know what? Let me actually just take the bias as 1. Let's take the bias as 1. So plus 1. So our y cap is going to be 0.04. So after that, we'll calculate our loss. So our loss is equal to half of our original y, which is 1, minus y cap. So our y cap is 0.04 minus 0. Sorry about that. My thing is glitching out. 0.04 the whole squared. So this is going to be half of 0.96 the whole squared. And this will approximately be, let me just take out the calculator. Yeah, it is going to be 0.4608. So with one sample, we've completed the forward pass and we've gotten our loss as 0.4608. Now I'm going to show you the same method, but we're going to do the forward pass using the matrix form. So let me show you how this looks. So since we're taking one sample, our x is going to be 1 cross 2, since it's only one sample. We've got x1, x2. Then our weight matrix is going to be 2 cross 3. W1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. Then we got our biases. We've got the second layer weights and the second layer bias. So how is this going to look? So this is going to look like, so our x will just fill out the values. So our x is 1 minus 1. Our W1 is going to be 1, 0, minus 1, and 0, 1, 1. And our bias 1 is just going to be all zeros since we took it as all 0. Now we're going to calculate the A matrix. So the A matrix is just going to be, A is going to be tan H of XW1 plus B1. So this is where matrix multiplication comes. So we know X is 1 cross 2. We know that this is 2 cross 3. So together we should get a 1 cross 3 plus our bias is 1 cross 1 1 cross 3. So we can add it up normally, and the tan H will apply to all of the elements. So let's just write that out. So A is going to be tan H of 1 minus 1, 1, 0, minus 1, 0, 1, 1, plus it's just 0, 0, and 0. So we're going to do matrix multiplication. So we take the row, multiply it by the column. So this is equal to tan H of, let's just do this, is going to be 1, because 1 into 1 is 1, and then we can ignore 0, and then this will just be minus 1, and this will be negative 2. And tan H applies to all of these elements, so that's just going to be, we're just going to get back the same thing. We're going to get 0.76, negative 0.76, and negative 0.96. Then our output y cap is just going to be AW2 plus B2. So we know A is 1 cross 3. We know W2 is 3 cross 1, and our B is just going to be 1 cross 1. So again, we're going to do the matrix multiplication. We've got, 0.76, negative 0.76, negative 0.96, multiplied by our weights, W1, W2, W3, which is, let me just, oh yeah, we've taken them all as 1, plus our bias is just 1. So this is going to be, so our y cap, which is also going to be just 1 cross 1, is going to be 0.04. Now for the loss function, we've taken loss as half of y minus y cap, the whole squared. To write this in matrix form, this is essentially just L is equal to half of y minus y cap into y minus y cap transpose. So this is the matrix form of the same loss function. So if we calculate it, it's going to be half of 1 minus 0.04 into 1 minus 0.04 transpose. So this is just going to be half of 0.96. And since it's just 1 cross 1, the transpose is the same into 0.96, which is ultimately the same thing we end up with. We get 0.4608. So this is the matrix form. So you might be wondering, why use the matrix instead of, the algebraic method? So let's say you had 300 sample points. So if you were to do it algebraically, you'll have to run a loop for 300 samples. So you'll have to do it 300 times. But with the help of matrices, matrix multiplications can be done really easily by the GPU. It can be done parallelly. So this is the reason why we prefer matrices. So suppose we had a data set of 300, our x would be, the only thing that would change is our x dimension. It would just be 300 cross 2, but everything else will remain the same. This will be 2 cross 3. Our bias will get repeated multiple times for each sample, but it'll be the same value. So it's going to be, so this will be 300 cross 3. So this previously was 1 cross 3, right? It's just going to be 300 cross 3, our bias, but the values will be just repeated. So suppose it was B1, B2, B3, right? So it'll again be B1, B2, B3, and this just get repeated like 300 times. Everything else is the same. So yeah, that's basically the forward pass in matrix form. Now we'll get into the crux, which is the backward pass, which was the main topic of this video. So I'm going to do the manual backpropagation algebraically first, and then I'll show you the same thing in the matrix form. And after that, we'll move on to the code. All right, now we're finally going to move on to the backpropagation. So I've just brought the network here. So what we're going to do is we need to update the weights, all the weights technically. We need to update W11, 12, 13, 21, 22, 23, and then W1, W2, W3, and as well as the biases. So we need to find the derivatives with respect to that. And we're going to be following the gradient descent algorithm. So essentially what we need is, so the new value, so for W11, I'm going to call it dash, or yeah, let's call it dash, is essentially just your W11. This is the current value minus your learning rate. This is eta. It's your learning rate multiplied by your derivative, partial derivative of your loss function with respect to this particular weight. So this is how it's updated, and you need to do this for every single weight. So it's the same formula except the things get changed. W11 will be 1, 2, so on and so forth. So how do we exactly do this? So this is where the chain rule comes into play. So for simplicity, remember how I wrote A1 is tan H of the whole thing, like it was W11x1 plus W21x2 plus B1. So we're going to call this whole thing that's in brackets, we're going to call it just Z1. So it's easy. When we take partial derivatives, I can show it to you properly. So if we take the chain rule, essentially del L by del W11 will be your loss function with respect to, if you take the derivative, sorry, with respect to our prediction, we multiply our derivative of our prediction with respect to A1. We're just following the chain. We're moving literally backwards. That's why it's called the backpropagation. Then we multiply that with our partial derivative of A1 with respect to Z1, and then multiply our partial derivative of Z1 with respect to our weight finally. So how is that going to work? So del L by del y cap rather, is your derivative of half y minus y cap, the whole squared by del y cap. So the derivative of this is just y minus y cap. Then we need del y cap with respect to A1, del of A1. So this is your, what is y cap? Y cap is our, if you recall the equation, it's A1 W1 plus A2 W2 plus A3 W3 plus B. Again, I'm not writing the layers because that'll just take too much. So the derivative of this with respect to A1. So if it's with respect to A1, partial derivative, everything else is a constant except for the A1 term. So this essentially just becomes del A1 W1 plus del A1, and this is nothing but W1. Good, now we found this. Now we need del A1 with respect to del Z1. So del A1 is nothing but tan H of Z1 divided by del Z1. So the derivative of tan H of Z1 is just 1 minus tan H squared Z1. That's just the derivative. And then finally, we do our del Z1 by del W11. So our Z1 is not A, sorry. It's W11 x1 plus W21 x2 plus B1 upon the, again, partial derivative with respect to 1, 1. Same logic, everything else is constant. So this just becomes x1. So now we can find del L. So del L by del W11 is nothing but, okay, we're going to need the first one, which is y minus y cap into, what is the next one? W1. So it's W1 into, it's going to be 1 minus tan H squared of Z1. Let's add one more bracket. Yeah. And into x1. Now we just substitute the values that we have. We know that the true value of y, wait, let me just refer to my notebook again. Yeah, wait, what did we calculate? Y as y minus our actual y. Let's go back to this. It's 1. Okay, right. So this is going to be, oh, sorry about this. Yeah. 1 minus our y cap, what we got is 0. Our y cap is 0.04. Okay. So 1 minus 0.04. Then it's going to be yeah. Oh, wait, hold on. I made a mistake. Sorry. This is going to be -1. Yeah. Sorry about that. It's partial derivative with respect to this. So this is negative of y minus y cap. Sorry about that. Okay, now let me just write out the values. So 1 minus 0 point negative of this. Then, this is, yeah, multiplied by our W1. Oh, so our W1 is just, 1 second. Yeah, our W1 is just 1 into 1 minus Z1 is, let me just go back. We have calculated A1, Z1 is just 1 again. So 1 minus tan h squared of 1 multiplied by our input x1, which is also just 1. So we get this to be approximately negative 0.4055. So now what we do is we update our W11. So our W11 new, I'm just going to call it dash, is just going to be 1 minus, if we take our learning rate as 0.1 into our derivative, which we just calculated, negative 0.4055, and we can see our weight got updated to this. It's approximately 1.041. So this is how the weights are calculated, the new weights. So we repeat this again for all the weights and all the biases. So again, this is just the algebraic way. Now I'm going to get into how to do it with the help of matrices. So let's do that. All right, let's do the matrix backpropagation. But before that, there's one thing I wanted to point out. Over here, if you look at it, 1 minus tan h squared z1, this is essentially, let me write it in a different color. So this is essentially tan h of z1 the whole squared. So we know that tan h of z1 is nothing but a1. So it's essentially just a1 squared. So this whole expression, 1 minus tan h squared z1, is just 1 minus a1 squared. All right, now how do we do this in the matrix form? So it might seem a little bit complicated. Like I won't deny that. It does seem a bit daunting. But let me explain how the matrix form is. So essentially, rather than taking it individually, we've clubbed it into a matrix. So we need the matrix for each of the ones. So we know in matrix form, we have W1, we have W2, we have B1, and we have B2. These are all matrices, and we have our X matrix. So we need dW1. So dW1 is essentially just the partial derivative of the elements. So it's dl by dW11, del L by del W12, del L by del W13, and then similarly, yeah, W21 dot 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 dot. And then yeah, dW2 is again you just fill out the matrix, that's it. So if whatever our W2 matrix was, just the partial derivative of that. So this would just be W1 by del W2. This is also second layer, and del L by del W3, second layer. And the shapes will be the same as the corresponding matrices. So W2 shape was also 3 by 1. DW2 matrix shape will also be 3 by 1. Now don't get too caught up in all of this. I'm going to show you the derivative calculation using the matrices. So let's do that. And don't worry too much about it. A lot of this will be taken care of in the code, but this is just for your understanding. So what do we need? So we need dy cap. So our dy cap will just be, well, del L by del y cap, which is just y cap minus y. So this is just negative 0.96. We've calculated this previously. Similarly, we can fill out dW2. I've already done the calculation, so I'm just going to like write out the values. This will be negative 0.7. Again, we use the chain rule. Actually, you know what? Let me, before doing that, let me just write it out. So our dw2 would be this. Hold up. Yeah, it would be a1, a2, a3 into partial derivative with respect to y cap. So we get our values. So this will be 7296 positive 7296 and 0.9216. Similarly, we're going to find db2. So our db2 is just going to be dy cap. Again, if you just take the derivative, you'll understand. It's just filling out the partial derivatives. Then we need dz1, which is just dl by del z1, del l by del z2, and del l by del, sorry about that, del l by del z3. So yeah, this is essentially just going to be, we're going to use chain rule again. So it's going to be dy cap w2 transpose into 1 minus tan squared h. So minus tan squared of z, the z matrix. So as I told you earlier, the tan h of z1 is just going to be a1. So here, since it's the whole matrix, so it's just going to be the a1 matrix, the whole square. I'll tell you what this symbol means. So the symbol is just basically element-wise product. So this is just going to be 0.96. Oh, sorry about that. Then it's going to be negative 0.96 and negative 0.96. And we multiply this by 0.4224, 0.4224, 0.0784. So that again, so this symbol just means pairwise. So we multiply this with this. So this will be negative 0.4055. Then we multiply this with this, which will again be the same thing in this case. And then we multiply this with this. So that's going to be negative 0.0753. So similarly, we repeat the calculations and we get dw1 matrix and we get the db matrix. So I'm just going to write down what dw1 is, and I'm going to show you how it's updated. So similarly, again, we use the backprop and everything. And yeah, not backprop, sorry, the chain rule to get the answers. Oh, sorry about that. This will be 0.753. And this will be 0.40 positive. Again, the same 0.4055. And this will be 0.0753. So our update, so our W1 new is going to be a W1 old into 0.1 DW1. So W1 old is, so this is just going to be 1, 0, negative 1, 0, 1, 1 into 0.1 of DW1, which is given here. So I've already done the calculation, so I'm just going to write it out. So your W1 new is going to be 1.04055, 0.0405. This will be negative 0.99 approx. And then this will be 405, 0.95, and again 0.99 approx. So these are the new weights. And if we just look back at our manual backpropagation, this is exactly what we got, 1.04055. So yeah, so this is how it's done using matrices. So matrices help do all these calculations very quickly, especially when the batch size increases. So right now this was just for like one specific sample. So imagine this with like thousands and like millions of samples. So that's why matrices help simplify that, because the GPU can do matrix multiplication parallelly. So yeah, this is how it's done. Now I'll just move on to some code and show you how it works. All right, so here I've basically built out the notebook already. So whatever we talked about in this video, I've just made the entire thing into a notebook. So it's the same process. Here we're going to create the data set. And the difference here is we're going to sample uh, from normal distribution. Then we're going to normalize the inputs. This is how you normalize it. So let's look at it visually. So if you look at it, this is how it looks. Our data points, there's 300 samples here. Then we apply the same thing, the tan age activation and everything. We get our W1, W2, our initial initialization that we've done. And then this is the epoch done manually. Again, I've written out all the formulas and everything. I encourage you guys to go through this notebook, but yeah, all this is what we've done manually. So just go through the code, just see how it is. I just want to show you the NumPy model. So yeah, here's the NumPy model. We can see with more number of epochs, the training loss is reduced. And yeah, there we go. This is our original data. This is our NumPy's model of it. And then I've just recreated the same thing in PyTorch. And finally, there we go. This is ultimately what we've gotten. So yeah, I recommend you just go through this code. I'll upload it to my GitHub. And yeah, like practice it on your own. Try to do the calculations manually. And yeah, it's just about repetition. And then once you get a hang of it, it'll come to you. So I hope you guys enjoyed this video. Let me know what you want me to do next. And yeah, I'll see you guys next time.